All right, welcome everyone. I'll just give everyone a few seconds to settle in, and then we'll start our presentation on Emotet, Emotet Exposed, looking at a very long-living and famous malware as a service distribution platform, and that's why we called it here the cyber criminal supply chain. It's really a part of the infrastructure that the bad guys use to deliver malware to infected machines. All right, so let's get started. Hello, everyone. My name is Chris Krugel. I'm VP Security Services in the Networking and Security Business Unit at VMware. I joined VMware a few years ago as part of an acquisition of Lastline. I was one of the founders, and we were doing network detection response. So I have a long-standing interest in malware. I'm also a faculty member at the UC Santa Barbara. So research, malware, and cybercrime is an area that has interested me for a long time. And I will give this presentation together with Giovanni. Giovanni Vigna is here, and he'll introduce himself when the second part of this presentation starts. All right, so let's jump right in. What is Emotet? It's, as I mentioned, it's a very long-lived botnet. It's, I think, a true implementation or incarnation of what we'd call an advanced persistent threat. It has been around since about 2014, and it has been very resilient and very advanced in the ways that it has stayed alive, that it has camouflaged its command and control infrastructure, and that it has tried different ways in infecting users. It's controlled by a group that is called either Mummy Spider, Mealybug, or TA542, and it really started its existence sort of with humble beginnings in Europe as a Trojan that was focusing on banking information, banking logins. So here you can see a little bit of a timeline, and you see Emotet appearing almost 10 years ago. As I said, it was focusing on stealing bank information. And it was interesting already at that time, so you could already see a little bit of the sophistication of the folks who were developing this malware, because they were not just injecting some stuff into the web pages to steal some credentials and banking information. They were actually doing it directly off the network traffic. So it was already kind of interesting and a little bit different. And as time progressed, the malware authors started to expand their geographical scope a little bit from Central European, German region to broader US, also Latin America. And they also started to drop different versions that made it harder to detect and made it more efficient in spreading. And in fact, over the years, it became so effective that the focus shifted from, hey, instead of just basically being a banking Trojan, it became more a delivery infrastructure, really a malware as a service delivery infrastructure where it could be used, so the infections could be used by other threat actors to basically drop malware on machines where Emotet was running. And so that was sort of an evolution that started around 2017, and it was used by a number of sort of well-known, interesting information stealer like TrickBot, for example, or QBot, as well as some ransomware, right? And so it became such a nuisance that actually there was an effort, a deliberate effort to take it down, which is something that happened in 2021 with Operation Ladybird, and that was an interesting collaboration between US and European law enforcement and Europol. And some might still remember there was this interesting video that the Ukrainian police shared where they basically raided the home of the folks that were supposedly running Emotet, and there were the gold bars and the cash and everything. And of course, at least these couple of guys were then apprehended and put in jail. And the good thing was that takedown actually worked, at least for a while, right? They didn't only sort of jail the folks that were supposedly running it, they were also deploying commands that were instructing Emotet to sort of delete itself or uninstall itself. And it was sort of all was great for a while until later that year, sort of late 21, it was TrickBot that was suddenly starting to deploy Emotet DLLs. It was sort of like a reversal where initially Emotet was dropping TrickBot, and now TrickBot was dropping Emotet DLLs and basically restarted the entire botnet. And this is sort of the time when, we have been observing Emotet for a while, but we also saw that resurgence, and we sort of decided, okay, it's maybe a good opportunity to study the infrastructure and the malware in a little more detail, and in fact, that's when we set out to study for about a 6-month period from the beginning to the middle of 2021. The botnet, its sort of execution and spreading mechanisms, and its back-end command and control infrastructure in much more detail. And what is also interesting, just sort of for completeness, there are always these waves that Emotet was not always running. These guys were, we don't know exactly, but sometimes taking vacations, they were pretty successful. So then they stopped doing something and then it came back. And also like late last year, there was sort of a drop in its activity. And if you looked at some of the news, actually just in March, it came back again and had a different way of having an evasion with a very large zip file where there was a Word document in there. So it's quite interesting, and it really has undergone a lot of changes over time. All right, so how does it spread? It's based on emails, spam emails. It's basically sending a lot of spam emails and try to trick people onto clicking on attachments. Sometimes it also includes links that then point to documents, but often the documents, the malicious documents, are directly embedded as attachments. And what is interesting is, it has been known and does is still known to make use of sort of macros in different ways, right? VBA scripts and Excel4 macros and different ways in which sort of those macros are camouflaged. And there's always a little bit of like innovation going on in the way the malicious code and these attachments are sort of evolved to bypass defenses. And there was even some interesting situation where Microsoft at one point said, okay, we're going to forbid everybody by default to run these Excel4 macros, right? And then they say, well, maybe we shouldn't do that. And they say, no, we should really do it. And of course, in the end now, I think it's off by default. But then Emotet tries to trick users into actually enabling macros again so it can continue to happily get executed. So if you click on that document and you open it and you run the macros, what would happen then is those macros would try to download the DLL, the actual core DLL of Emotet, which is essentially the core piece of the malware, as well as additional modules. And it uses maybe PowerShell for it, or a number of other built-in Windows services, registry service, for example, to run and load those DLLs. And as it sort of loads these additional modules, and we'll talk about these modules in a little more detail, it also then has the opportunity to download additional other malware, as I mentioned, for example, other information stealer or ransomware components, right? That's sort of the idea. And what was also maybe worth mentioning and interesting, there was actually a tweet coming out today from a researcher at Google, because obviously it sends a lot of spam emails. So if you're working for Gmail, then you see a lot of this stuff. And they were actually talking about the different ways, just in some presentation, I think, yesterday, of how they try to use AI to detect to quickly detect if there are some malicious documents being sent. And in fact, in some prior research, we have also worked quite a bit on trying to understand those Excel4 macros in detail and sort of peel back all the layers of obfuscation they have put out there. So very, very interesting in sort of how a very simple spam-based spreading mechanism can actually have various layers of interesting obfuscation and defenses. All right, so when we look at sort of the study, that is called here Emotet Exposed, as I mentioned, we look at some of the things the actual DLL or the Emotet binary does, and I will talk a little bit more about that. These are the modules that it downloads, as well as what we call here the execution chains or execution traces, because it's not just a DLL and then there's a DLL that is running. It actually often includes a number of components that are being executed in a chain, or it's almost like a tree where one Windows binary like PowerShell is used to launch a couple of processes, then those processes in turn spawn other processes, and you get a fairly complicated chain of executions of those programs. So we'll look at those, and then I am sort of handing it off to Giovanni to talk more about the infrastructure lifecycle and sort of how the back end of the system works, how its command and control service works. And a lot of the analysis that we have done is through, some others, of course, have done this before, but was through sock puppets, where we basically re-implemented a a client faking to be Emotet that was downloading some of these modules and interacting with the command and control infrastructure so that we had always a fresh stream of, for example, modules that we could look at, as well as some of the command and control infrastructure that the malware was communicating with. All right, so let's dive into the first. We call this, by the way, the reloaded modules because it's Emotet reloaded after its resurgence. So what are the modules? Not surprisingly, since it spreads by email, a lot of the modules are focused on that problem of getting valid email addresses, finding credentials maybe to someone's emails accounts, and sort of spreading by spamming, right? Sending the actual spam email. So what you can see here, right? So there's of course a core module, but then you have the spamming module, and then on the right side you see a bunch of modules that are used to, for example, steal email accounts from popular email clients like Outlook and Thunderbird. There are a couple of actually legitimate tools from Nearsoft, the Mail Pass Viewer and the Web Browser Pass Viewer, where it tries to obtain username password combinations that you have on your local machine. And then on the left, that's a kind of like interesting, more updated, newer modules that were adding a spreading component to Emotet, or expanding on a spreading component that Emotet had for a while, that is going beyond just spam, which is using local SMB shares, where it basically tries to see, okay, are there any open connections to some SMB servers? Can I just use that to drop it? And if that doesn't work, I start to brute force a little bit with some usernames and passwords. But it's basically adding a lateral component, so not just email-based, but it has a lateral spreading component as well. And finally, there is a credit card information stealer that is particularly targeting Chrome. And the idea here is basically, almost like going back a little bit to the original bank info stealer days, where you try to obtain some credit card information from the browser. Okay, and so as I mentioned, we have this sort of little client, this sock puppet, that is now going and downloading modules as much as it can, right, over this 6-month period, and try to say, okay, hey, can you give me your latest modules? Can you give me your latest modules? And then we could basically study those modules and try to understand, okay, which ones are popular? Are there any similarities? How do the malware operators generally deal with those different modules that they want to load into an Emotet infected machine? So we look at this, and you basically can see here a list, or maybe you can't see it in the back because the font is pretty small. But what you can basically see here is that every time, so each line, a module is being shipped, if you just hash it, it will look different. So it's not too surprising, right? Some polymorphism happening in the code. But what it turns out actually is, no, it's not really polymorphic code. They just have some small piece in the data section that is different all the time. So if you actually just hash the entire file, it will look different. But if you strip the data section and you're just looking at the actual code, you will find that the hashes do often match. And in fact, I think this is something that we called here conceptual hash, where basically the code is identical. And in the color coding, you would see the same color would be when the file has the same conceptual hash. So basically, it's the same code, but with that sort of noise removed from the data section. And that allows us to study a little bit better, okay, so when do they actually change the code over time, and when do we see a new version, rather than just saying, hey, every file is new, right? That's not super helpful. I also want to point out, and that's kind of interesting in the context of that sock puppet, again, it's a little bit hard to see, but on this table, we also have listed the volume name of the disk as well as the computer name. Why is this important? It's important because that's the way Emotet assigns IDs to its infections. And if you basically write this little client, the fake client, and it always sends the same data, they will very quickly determine, well, this is kind of weird, right? There's this one host that seems to be infected, and that's awfully often requesting some modules from us. So we want to avoid this, so you randomize it, you randomize your source IPs a little bit, and then you get a nice stream of new modules and new data. Okay, so when you then look at the timeline, and we're sort of showing here, it says Epoch 4 and Epoch 5. That's, I think, a concept that Giovanni will talk much more about. It's basically a way of characterizing their backend infrastructure, where you have a set of sort of backend IP addresses that are called epoch, and unlike a normal epoch where you had one that follows another in time, right? They actually overlap, and so you could really see as if there are sort of two different sets of command and control IPs that are basically forming two separate and distinct backends, almost like you have two separate botnets that are operating. And you can see here they're operating actually during that same time period, and we will see that, hey, they download different types of modules to or through these two different epochs. And sometimes or often there was actually the first version of a particular component rolled out on Epoch 4, and then it was moved over to Epoch 5. And some thoughts are maybe Epoch 4 is like a test net, right? Like if you're doing some development on Ethereum, they also have a test net, right? And then there's the main net, and maybe you try out a few things, and then you move it over to your actual test net, to your main net. Okay, and so when we look at the actual modules, you can see them here in sort of the different colors in the different rows. Here for Epoch 4, here for Epoch 5. They look somewhat similar, and what you can see is two things. One is the core module, which is the pink one on top, is always shipped. Many of the spam modules and the sort of email address stealers are always shipped. And then some of the other modules, like the credential theft or the lateral movement, is less often shipped and might also undergo a little more modifications over time. And again, it's not super surprising because, as a spam botnet, obviously you want to steal email addresses and spam. What would be interesting here, these gaps, maybe that's something that Giovanni will also talk a little more. They actually changed their way. They were encrypting or obfuscating the way their configuration files were handled during the study period, and it took us a little while to catch up, and sometimes the collection infrastructure had a little bit of a failure. So there are some gaps, and just shows, in the real world, some stuff can go sideways, so we don't have like perfect bars here. Okay, and so just to finish this and show you a little bit how distributed the delivery infrastructure of those modules is. You see here the different lines, each are different AS. On the right side, you see the number of different modules that come from a source from each of these ASs, autonomous systems on the internet. And you can see here that there is some set of IPs in a certain number of ASs that deliver the bulk of those modules, but there's a fairly wide or long tail, I should say, where there's a lot of sort of smaller infections that deliver still a bunch of modules, but then they are mostly core or spam modules, while the ones that are more active in distributing the modules, those, of course, have the full range of all the 8 modules that we have talked that are being delivered. Okay, it just shows, it's a very resilient and a very distributed infrastructure using here in this particular study period, IP addresses that were located in ASs, I think in Southeast Asia and Africa and the US. Okay, so then let me talk about the execution event. So now we have these modules, but how do these modules get loaded? Well, we sort of said, first you have to click on something, you have to click on a document, and then we have this chain of programs that are being launched in response to the macro that is being executed. And we capture that in our sandbox. So when we execute the macros in the document by basically pretending to click on it, we have our sandbox, and we can analyze in a great detail, okay, so how is the actual infection unfolding? Like, okay, typically you have excel.exe, because it's Excel, so Excel starts when you click on an Excel document, and then you see things like maybe the scripting host, or you see run DLL when a DLL is being run, or you see register server when you register a DLL, right? So you see the different programs that might be involved, but there are sometimes also other sort of intel gathering programs, like ping is checked for network connectivity, right? And so you're basically seeing this whole sequence, or really rather say tree of program executions that are launched when a victim clicks on that malware, right? And so while we call it here an execution chain, as I said, it's really a tree. And the interesting question now is, are these trees or are these sequences of execution different or are they the same throughout this whole study period? And in order to sort of understand this a little bit better or look at it in a little more systematic way, we introduce or we use the notion of a tree edit distance, where we're basically saying, hey, we have these trees, and well, in order to determine the distance between two trees, you could say, how many changes do I need to make to one tree to get to another tree? And I call this the edit distance, the number of edits, the number of steps I need to take to make these modifications. So when you see here A and B, the trees look pretty similar. You just see in the bottom right corner, it uses PowerShell in one and RegServe32 on the other. That is an edit distance of 1. You just change that node. Now the tree A becomes B. Of course, between A and B and C, the distance is bigger. And so you can then cluster or group those execution chains or trees and determine their similarity or dissimilarity based on the notion of edit distance, right? And so, okay, so first let's look at the data set. We had about 20,000 samples here that had some interesting execution chain, and we got, I think, 139 sort of unique program chains or unique trees out of this. And we call this a program chain when we just look at the actual program that is being run. There's also an invocation chain when we actually say, okay, two nodes are the same not only when their program matches, but also when the parameters are identical. And obviously, when parameters are used, then it's very much more diverse, right? It's very unlikely that you have exactly the same parameters on some invocation. So you get more than 20,000 of these. And if you're really observant, you're wondering, like, how can we create more than 20,000 unique invocation chains out of 19,700 samples? And the reason is actually we run it in Windows 7 and Windows 10. Sometimes the chains are different, so there could be one sample that actually creates two different chains. All right, so now we basically have those, and the first question that you want to maybe know is like, okay, so how many unique trees are there, or unique chains? And you can see it's a fairly long tail, but you have a few trees that are really dominating, right? That are basically making up, I think, about 80% of all the executions. And as you can imagine, those are somewhat short, small trees where it just takes the DLL and runs. And more in that long tail, you have more complicated, more involved chains. But as we will see, they do experiment with these different execution chains. And I think it's also important because when you're an EDR vendor, those sequences of execution are really a signal that you try to pick up on, right? And you say, hey, if these programs are launched in this order, maybe this is bad, maybe this is AMOTET, right? And so they have to rotate, they have to change this in order to be able to stay under the radar. Okay, and so when we look at now, or sort of trying to cluster these trees and draw them in a confusion matrix, then you get these pictures, left for the program, right for the invocation chains. And just to sort of walk you very quickly through it, you basically have a matrix where you compare each tree with all the other trees, sort of along a row. And across the diagonal, you have sort of a white line because each tree along the diagonal is similar to itself, right? And what you will start to see is you see these clusters, these bright clusters, where those clusters are very, very similar or almost the same tree. And you see sort of the big clusters that really represent, obviously, exactly those groups that we've previously seen before as the main similarity trees. And so, that is in some sense a reinforcement of what we've just shown you in the table. But what is interesting, or maybe more interesting, is if you draw the similarity across time. So this is now on the x-axis is time. And what you see, or what you could expect, is that it all looks random, but in fact, it's not. You really see groups and clusters of samples along time as well. And these are sort of new versions and new iterations as they come out over time. And that is also confirmed here when you sort of have timelines of samples. And that's my last slide before I hand it off to Giovanni, where you can see a lot of experimentation in sort of the early days when they come back. And then you sort of have a few dominant winning execution trees, execution chains, and those are sort of the ones that really survived over time. So that's, in some sense, studying the programs, the executions, and the modules. And with that, I hand it over to Giovanni for the infrastructure lifecycle.
Thank you.
Thank you.
You guys hear me okay? People, I should say. So this is interesting for us. First of all, I'm Giovanni Vigna. I am Senior Director of Threat Intelligence at VMware, and I co-founded Lastline with Chris here, and we became part of VMware as Lastline was acquired in 2020. So at this point, we're going to switch gears a little bit, and we're going to look at how the infrastructure in the backend works. And this is interesting because it's one of the most resilient and long-lived infrastructures, so we really try to understand how it operates. Even though sometimes we were baffled. There are things that we don't know. Sometimes we see behavior and we're like, what? And sometimes could be that, you know, bad guys are people too, and they get sick and they don't repair their infrastructure, or they lose control of it, or there are fights and they split and things like that. We have little to no visibility. There's some anecdotal evidence every once in a while, but for the most part, we have to look at the data and trying to understand it sort of like black box style. So first of all, how do we get this data? We look at the infrastructure by taking the DLLs and analyzing them to extract the IP addresses and ports that the DLL use for command and control. So you have to understand that the DLL, when you receive the Emotet DLL, nothing is, you know, in the clear. The DLL, the core DLL, has another DLL inside, and in fact, we use our VMware Sandbox to extract and unpack the second DLL. Then the list of IP and addresses are obfuscated, so we have to develop techniques to extract that. And in fact, one of the gaps, the bigger gaps that you've seen in our analysis, was due to the fact that at a certain point, the bad guys, you know, realized that we were, no, not just us, but the community got to the point where it was too easy to decrypt and extract the IP addresses and port, and decided to radically switch the way in which they were obfuscating their IP address and port. And instead of having them in a list, they sort of like turn the data into code. So every time you want to get an IP address and port, you would call a function, and the result of the function would be this IP address and port. And fun fact, the beauty of it, if you guys are malware analysts and you look at this malware with IDAPRO, it was amazing to see these very complicated binary functions. When you ask IDAPRO to decompile, it will be just return this value. So there was a lot of obfuscation, a lot of fake code that was introduced just to make the whole analysis more difficult. And you can see here that we have, first of all, two sets of things. We look at the origin of the DLL. Some of the DLL actually arrived through a complete infection. So we had the Excel file that dropped eventually the DLL, and some of them were just submitted through the API, because we provide, as part of our solution, the ability to just use the API to submit to the malware analysis system samples. And in those cases, obviously, we don't have the complete chain. We have only the actual DLL. And also, we have both 32-bit DLL, and in the later part, the 64-bit DLL became more prevalent. And you can see it here, the differentiation between the two. And this is to characterize the data set that we used. Of course, we talked about epochs. We have epoch 5 and epoch 4. Those are characterized actually by the encryption keys that they use to validate communication and encrypt communication to the CNC. Keys have not changed in quite a bit. And this allows us to understand exactly what kind of infrastructure they use. So epoch 4 is the first they appeared, and then epoch 5. Also, if you look at the breakdown, the distribution of IP, they're slightly different. The interesting thing that you can see that there is one single IP address that is shared between these two epochs. Okay, so they have vastly different IP addresses. So they run 200 for epoch 4 and 127 that we observed for epoch 5, but they have only one shared. And you can see that also the distribution of the DLL is kind of different. You can see that we have more epoch 4 documents and almost the same in terms of the actual DLL between the two. But this tells us that we have actually, these 328 unique addresses that we have to follow and characterize. So first of all, we'll say, how are these IP addresses appearing? If you see, for example, if you look at the number of IP addresses, we have between 20 and 63 with an average of 47 in each DLL. So each DLL comes with a set of these IP address and port combination. And here you can see the distribution. There are certain addresses that are used in thousands of these DLL, and then others that are used less. Obviously, you can understand that this is due to the fact that these IP addresses are continuously cycled. So there is the usual cat and mouse operation where the bad guys set up infrastructure, the good guys start blocking, and so the guys find new IP addresses to be used, and so on and so forth. And actually, if you look at the frequency of specific set of addresses, it's actually very different, meaning that it has a long tail of various combinations. There are a few example that you see towards the left-hand side that are very frequent. So there are some combination that were particularly successful and they were used over and over again throughout infection. For some reason, they were able to avoid detection. So you can imagine that certain technique, and we will see more when we see other graphs that combine the way in which the DLL is delivered with the network infrastructure. But the cool thing is to understand that if you have a set of IPs that is used and reused continuously, that also mean that the way in which those DLLs were distributed were not being, was very successful. So the DLL were not caught, the infection was not detected, and those IP were not becoming part of the blocking address, so they didn't need to be recycled, and therefore, of course, they will be reused. So here we did something because we want to understand more in groups, and since there was such diversity in the sets of IP and addresses, we say, okay, can we cluster them together to characterize better the network infrastructure evolution? We need to find a way to put them all together. And so we thought for a while, do various possible techniques. And then we actually settled on something that we haven't seen been used before, which is to use an algorithm that is actually used for PageRank in web searches. It's called TF-IDF, term frequency inverse distribution frequency, which is a way to kind of take a document, look at the words in it, and create a vector that kind of gives higher values to the words that are more characterizing a certain document. They're more rare and they appear so only in certain documents. So we use that measure, that vector. We use the difference between vectors is called cosine similarity. Can be a little technical, but it's just to say how close they are. And we use an algorithm called dbScan to create these clusters. So at the end, we ended up with 13 because we start from 0 because we're computer scientists. We had 13 clusters of this group of IP addresses and port, and we start tracking those because we think that these are really associated with specific campaigns. And actually, you can see here that if you actually plot them on a timeline, you can see different operations, different campaigns that happen. For example, if you look at the green campaign, that was a not very successful campaign. It was long-lived, but what you see is that they have to cycle continuously through new IP address combinations because they were continuously detected. The IPs were extracted. They were included in block lists and other type of intrusion detection solutions, and as a result, they had to change. While you can see other campaigns, for example, the yellow and the red, where things were added and were never taken out. And you can see that they have long-lived infrastructure that was not taken down. And this really, this is an example, for example, of this group of IP addresses that were particularly resilient and were inserted and lived a long time, which is, a sign that something is working for the bad guy and not working for the good guys. This is also the same thing for Epoch 5. The interesting thing here is that you can see that there are a little more, I would say, apart from the red campaign here, there was a little more stability than Epoch 4. And the interesting fact is here that we think that they're using Epoch 4 really for testing. And we see a lot of very short-lived attempt and campaign on Epoch 4, a lot of churn, and we think that that's very much associated with the testing of new techniques. And then when they find the right technique, the right evasion that is able to counteract the solutions that we deploy every day, then they move to Epoch 5. And you can see, for example, there are some of these campaigns that are, touch a lot of clusters, and are able to actually contain and represent and support a certain campaign for almost the whole duration of our study. If we look at where this stuff comes from, we see that it comes from various countries with a prevalence for the United States. This is not surprising because these IPs are not owned or operated by the bad guys. These are proxies to the real command and control that we cannot see. So as such, the bad guys want to infect machines in countries with good reputations, because of course, if you're in a company and you see suddenly an TCP connection to a host in Russia, you might say, we shouldn't be talking to a host in Russia, and could raise alarms. But of course, if you have these compromised hosts in United States, Germany, France, and so on, you can actually hide the sort of like the shadiness of your operation. And so this is the distribution that we observed. And also we have seen the distribution of ports. If you look at this, you will notice that the vast majority was actually port 8080 and not as much like port 80 like one would imagine. This is because, again, these cyber criminals are compromising existing machines. So suppose you're running something on port 80, your website, for example, or port 443, and people arrive and take over and run something they want on port 80, you would immediately notice because your website is not working anymore. So what these people mostly do is gain control of a host and run a parallel operation on port 8080 or port 443 in order to be able to run their infrastructure without being noticed by the legitimate owner of the host. Also, we look at the YARM or JARM fingerprint. This is a fuzzy hashing system that takes 10 or so interaction with SSL server to kind of understand what kind of combination of protocols are used by the server, and this can be really used to uniquely identify the type of infrastructure, the software that is running on the server side. And so in this case, we find that there are 14 hashes, but you can see that almost every single one was associated with a specific hash. That means that they continually reuse their software infrastructure. So when they break into a machine, they have a set of parameter, Nginx most of the time, that they deploy with the right, always the same type of operation. So they're very consistent from this point of view. Also, we looked at the prevalence of AS numbers, and you can see that their autonomous system, they're 144 unique, but with some really contributed the most, in particular DigitalOcean, which is not a bulletproof hosting provider, is just probably unlucky that to have a number of compromised hosts in their domain. And you can see that a lot of the ASs have a single IP address. This is typical of infrastructure that are based on compromised hosts. Because of course the compromising host is an opportunistic approach. They try large-scale exploit, and so they don't care about a specific AS. They don't want to, create a bulletproof hosting for this kind of proxy, but instead they spread throughout the infrastructure. And I think that one thing that was really interesting, and you can find this in the report, by the way, there is a report that you can find on the VMware Tau webpage that has a lot of details. In particular, has the details on how to develop your own sock puppet, so you can read the excruciating details of what it entails to create an infrastructure prober that can go to Emotet and extract this information. What is important here is that we created a graph that shows the sort of the association between the cluster of infection techniques and the cluster of infrastructure. And you can see, for example, if you see the beige big band there, almost looks like, okay, we found the right group of techniques to avoid detection. Let's deploy a new piece of infrastructure. Let's make that sort of technique widespread. And you can see there is an almost one-to-one association between the beige and the orange one. So these are really the cyber criminals trying new techniques, being very successful, and deploying ad hoc infrastructure to match that particular technique. But you also see things that, in this case, that contain a lot of different techniques. And these are usually testing infrastructure. So these are groups of network endpoint that are used by the bad guys to test their technique. And you can see each of these on the left-hand side, each of these kind of flows are specific type of techniques and sequence of execution, like Chris described, that are used for compromise. And you can see that in certain cases, there are dozens of those used for a single IP. And so this is interesting because really shows that they have, in the mind of the cyber criminals, they really have two types of kind of modes. They have testing modes in which they're continually trying new things. Then they find the right thing and they go in deployment mode with Epoch 5, with very stable IP addresses that they don't have to churn continuously because they found the right approach. So if you have to get an insight out of this presentation, is like we were able to characterize really the evolution of how the cyber criminals are trying different techniques, finding the sort of the perfect way to approach the evasion problem, and then move to a parallel infrastructure when they know that they can keep their network infrastructure stable and undetected. So I think this is very unique to this particular botnet, and it was very fun to analyze. So in conclusion, if you want to take the major takeaway, I would say the characterization of program chain as trees and being able to cluster them is really something that the community could use more, because it's not very often a signal, the specific shape of the tree that is used for detection, and we think that is a very effective way to characterize specific families. So not just if something is good or bad, what kind of family that is. These kind of chains are very characterizing. Also that they're, cyber criminals have really a well-structured supply chain with infrastructure that are used for test, for deployment, and that really care about having the right type of exploitation with the right type of infrastructure. As part of this research, we also find new modules. In particular, we found this, lateral movement, new modules that we were surprised to find. And at a certain point, actually, we noticed that we're trying to deploy C2 framework component like Cobalt Strike beacons and so on. And actually, this started a whole new research in our research group in characterizing C2 frameworks, exactly because Emotet started actually deploying this kind of malware. And, and of course, if you look at what we recommend for solutions, it's belt and suspenders. One solution is never enough. You need to have endpoint solutions. You need to have network solution. You need IDS, you need firewall, and you need them to talk together. Actually, there was one of the keynotes that was really covering how it is important not to have just one approach to security. Well, that's true. You want to have something that covers all your angle, and in the best of worlds is actually integrated to provide a single pane in which you can see all the activity. And this, that we just presented to you is the research that goes behind developing the solution at VMware. And with this, thank you very much, and we will take some questions.
Hey, thank you for the talk. I really enjoyed it. I have a question. So some malware, like for example Flashback, they do integrate a lot of their code in the data section itself. Did you see a correlation between some of the modules that were used, that were sideloaded as part of the botnet itself, as a correlation in the data sections based on which modules were loaded? So, for example, if I would say that if you found the similar hashes for the code itself, you could probably correlate it with the core module that was always loaded, and then the additional modules would probably be in the data section itself. So were there any correlations between the data section and some of the flavors of the execution trees that were there?
First of all, we didn't look at that correlation. That's actually a good suggestion. You have to understand that actually the core module actively contacts and downloads these additional modules to then loading it. So there is, we could look at specific correlation, but since the modules are not that many, we would identify, obviously the 8 or 10 possible correlation between the two, and it wouldn't be particularly characterizing in my opinion.
I see. Okay. Thank you.
Hi. Great presentation. Thank you. The IP port pair, is it safe to assume those are just boxes connected to the internet with no firewall and NAT? Like, how can?
Yeah, it is. These are hosts that were compromised. And therefore, they are active on the internet because they need to be contacted to act as a proxy to the actual CNC. So these are, poor fellas that got compromised and have Nginx installed, acting as a proxy to the actual back that we cannot see. That's actually something that the AS operators could see when they detect this thing, because they can see where they connect back.
Okay.
But I guess it's also true that often you have these ports like 8080, 443 just open by default, right?
Yeah.
And there's already a web server running, and someone puts in a firewall rule that says, yeah, you can go to 8088 and 443.
Yeah.
Maybe not all of them are used, but unfortunately, the rule is still there, so they just capitalize on it. But yeah, absolutely, it needs to be accessible from the outside.
And then servers are like PCs, laptops?
Good question. We have no real visibility of what if they are,
But I
pizza
think with
boxes or PCs.
Nginx and often in data centers, I would
Oh,
say.
you say PCs in terms of Windows machines.
Yeah, I know.
They're not end-user
Yeah.
machines. End-user machines usually are behind firewalls, and they cannot be reached. We didn't do a architecture analysis, but they're data center machines. Correct. The machine that gets infected is the user machine. So it's a user at home, receive a piece of email, the infection starts, the Emotet DLL unpacks the thing, say, okay, I'm going to contact this data center host and start downloading stuff to steal your password.
There's CNCs on the server, and the victims are the users, and then Emotet connects to that server to download additional modules or other malware like Qbot and stuff.
Oh, you're
Awesome.
welcome.
All right.
Thank you.
All right, thank you. Thanks, guys.
All right. Have a good one.